Dear friends, welcome to my presentations. I am working in Siirt University Department of Mathematics. I will talk about the new applications of the fractal fractional differential equations. I will give some main definitions. I will talk about the construction of the problems, and I will discuss the reproducing kernel Hilbert space method, the applications of this method to the fractal fractional differential equations, and some important references. The fractal derivative is a natural extension of Leibniz derivative for discontinuous fractal media. It can be categorized as a spatial local fractional derivative. Applications of this derivative to fractal media have taken much attention. For example, it can model heat transfer and water permission in multi-scale fabric and wool fibers. For fractional differential equations, we can say Lie will have searched an elementary fractional derivative and integral. The main goal for this research is to present the fractional calculus and to implement it to real-world problems. Another thing that we will use is the Laplace transform. Laplace transform is very useful transform to get the exact solutions of the problems. There are many works in the literature related to the Laplace transform. Some of them are given as. For example, Young has investigated the Laplace transform for approximation of highly oscillatory Volterra integral equations of the first kind. Talbot has worked on the accurate numerical inversion of Laplace transforms. Delgado et al. Have studied the Laplace homotopy analysis technique for researching linear partial differential equations. Yan has investigated the modified homotopy perturbation technique. And there are many other works related to the Laplace transform we can find in the literature. Fractal fractional differential equations are very remarkable topics nowadays. We investigate the fractal fractional differential equations by the reproducing kernel Hilbert space method and with the Laplace transform also. The reproducing kernel Hilbert space method, which calculates the numerical solution, is of great attention to many branches of applied science. Many works have been dedicated to the implementation of the reproducing kernel Hilbert space method to wide class of differential equations. The efficiency and the power of this method were considered by many others to research many implementations. This method is very effective method to solve many problems, and this method does not need any discretization to create effective results. We also studied the existence of the solutions to the telegraph equation in binary reproducing kernel Hilbert spaces with one of my collaborator. It's the important paper I suggest you to check. For the theory of reproducing kernels, I strongly suggest Aaron's paper. It contains many useful results, and also there are many applications of the reproducing kernel method in these references you can check. Now I will talk about some main definitions. In these references you can find these definitions in details. We assume that y of x is continuous in open interval AB if y is fractal differentiable on AB with order beta, then fractal fractional derivative can be represented with 1, where this derivative, fractal derivative defined by 2, assume that y is continuous in AB, then the fractal fractional integral is presented by 3. There are many kinds of transforms out there in the world. Laplace transform is the most important kind of these transforms. Let y be defined for x is equal to or greater than 0. The Laplace transform of y is defined by 4. This is just basic examples of the Laplace transforms. And we have the following relation for the Caputo derivative. The Caputo derivative with convolution can be written by 7. And we apply the Laplace transform and get 8 And we have the following relation between the Riemann-Leibel and the Caputo derivative. Sometimes we need to use this basic relation also. Okay, now we will talk about the three problems with the Caputo derivative. First, we consider equation 10. In here, we use fractal fractional derivative with the power law of kernel. And we can write this equation by 11 by the definition. Then we obtain 12. We use the relation between the fractal derivative and the classical derivative and obtain 12. Therefore, we get 13. And then we use the relation between Riemann-Leibel and Caputo derivative. We get 14. Then we will apply the reproducing kernel Hilbert space method to equation 14 to get the results. Another example, we consider 15. We use the same procedure and we can obtain 16. We use the relation between the fractal derivative and the classical derivative and obtain 17. Then we get the Riemann-Leibel derivative by 18 and we use the relation between the Riemann-Leibel and Caputo derivatives and we get 19. Then we apply the Laplace transform to both sides and we get 20. Thus, we obtain 21. If we simplify all the terms, we will get Laplace of y of x equal to beta times gamma 2 plus beta s to the minus beta minus alpha minus 2. Now we are ready to apply the inverse Laplace transform to get the solution. Then we will get the solution by 23. Another example that we consider in this work is this. We use fractal fractional derivative with power law of kernel. And we can write this equation like this. We again use the relation between the fractal derivative and the classical derivative. And we get this equation. This gives us the Riemann-Leibel derivative. And then we use the relation between Riemann-Leibel and Caputo derivative and get this equation. Now, I would like to talk about the reproducing kernel Hilbert space method. Then we will apply this method to the examples that we constructed in the construction of the problems section. We investigate our problems by the reproducing kernel Hilbert space method in this section. We construct some useful reproducing kernel Hilbert spaces and obtain very important reproducing kernel functions. We get the numerical results of the problems and we show them by the following tables also. We prove the accuracy of this method for fractal fractional differential equations with the power law kernel. This is our first space that we need, a sub 2 super 1. In this space, our function is absolutely continuous function and u prime is in L2. We need this reproducing kernel Hilbert space for the range. The inner product and the norm of this space are presented as. This is our inner product, this is the norm. Then we get the reproducing kernel function S. 1 plus x, 1 plus I. This is the basic kernel function that we need to construct the approximate solution by the reproducing kernel Hilbert space method. Another space that we need, a sub 2 super 2. In this space, u prime are absolutely continuous functions and the second derivative of u is in L2. And additionally, u at 0 equal to 0. This means this space satisfies the initial condition also. We we need this reproducing kernel space for the domain, and we have in a product and the norm like this. And this is the reproducing kernel function that we need to get the numerical results of the problems. Now, we construct our solutions in the reproducing kernel Hilbert space A sub 2 super 2. We define our bounded linear operator H from A sub 2 super 2 to A sub 2 super 1. Then our operator is equal to fractal fractional derivative plus m of x times y. Then we simplify the problem and construct 26. We construct phi equal to cxi, see our reproducing kernel function of the reproducing kernel Hilbert space A sub 2 super 1. Psi I is equal to its joint operator phi. And the orthonormal system can be obtained by the Gram-Schmidt orthogonalization process, and we get 27. Assume that y of x is the exact solution of 26. Then we will obtain the solution, series solution, with 28. Let's look at the proof. We will use the features of the adjoint operator and the reproducing kernel property to get the proof of the theorem. And also we use the property of the complete system and get 29. Now we use equation 27 and obtain 30. We know that psi I is equal to adjoint operator phi. Therefore we obtain this equation, and then we get this by the properties of the adjoint operator, and we use 26 and get this equation. At last, we obtain the desired result by the reproducing property, and this completes the proof. For the approximate solution, we use inter-interception of the terms, and we get this. We investigate 3 problems by reproducing kernel Hilbert space method. We demonstrate the numerical results of first problem by table 1. In this table, we find approximate solutions of the problem for different values of alpha and beta. Alpha is fractional order, beta is the fractal dimension. We present the numerical results of the second problem by tables 2, 4. In table 2, we show the absolute errors of the problem for different values of alpha and beta. In table 3, we demonstrate the relative errors of the problem for different values of alpha and beta. In table 4, we show the approximate solutions, exact solutions, absolute errors and relative errors for alpha equal to 0.5 and beta equal to 1. We present the approximate solutions of the third problem for the different values of alpha and beta in table 5. We choose 50 dense points for all our problems. We use Maples 18 to get the numerical results of the problems. We also demonstrate the exact solutions of the second problem by some figures. In the tables and figures, alpha shows the fractional order and beta describes the dimension of the fractal. And we give our numerical results for different values of alpha and beta. Therefore, we can say that we can see the effects of the dimension of the fractals also. This is the first table. In this table, we use different values of alpha and beta. You can see alpha beta equal to 0.1, 0.5 and 0.9. In the second table, we show our absolute errors for different values of alpha and beta. In the third table, we give the relative errors for different values of alpha and beta. And this is the approximate solution, exact solution, absolute error, and relative error for the second problem. For alpha equal to 0.5 and beta equal to 1. And this is the last table for alpha and beta equal to 0.5. And these are some references related to our topic. I strongly suggest this paper, Theory of Reproducing Kernels, Aaron's paper, and also suggest this work that we constructed with David Grove for existence of the solutions. Also, I strongly suggest the fractal fractional differential and integration by Professor Abdon Atangana. It's very useful paper for fractal fractional differential equations. And also, these two papers are very important for these topics. I strongly suggest you to read these papers also. Thank you for your attention.